Hello, everybody. Welcome to this session, which is around um, sports arena application. And maybe we can start. I have the honor to have two panelists today to exchange with us and exchange some experience. Maybe we should start introducing ourselves. Garrett, what do you think?
I think that works for me. My name's Gareth Collier. Since February this year, I've been the Sales and Marketing Director at NEXO. For the previous 10 years, I've been handling sales for NEXO in the UK market. Reinhard?
Yes, good morning to everybody. My name is Reinhard Steger. I'm a sales manager of Germany, and I'm working with NEXO for NEXO, I think, since the PS10 came up in 92 last century. And it's an honor to be with you there.
Thank you, Reinhard. My name is François Desfarges. I am head of engineering support at NEXO. I've been with NEXO, let's say, in a very consistent way since 2003. So I'm not as senior as is Reinhard. But anyway, I was there when the PS10 was launched because I used it also. So it's fact my story with NEXO is a lot longer. But anyway, a quick word on engineering support and on these sessions. This is the third cycles of seminar we're actually completing now. Engineering support mission is to serve all our customers. When I'm saying customers, it's not only our distribution network, of course, our distribution network we support very strongly, but also everybody who is involved with our systems. So this is sound engineers, it can be consultants, it can be designers, contractors. So this is our main mission. And among all the activities we do, there is this training part. And due to the current situation, of course, we are now developing a comprehensive program of webinars online. I hope this one will please you. I hope all of you are safe and doing well. And maybe one or two words on how we proceed. The first part of that session is going to be a PowerPoint I'm going to give you on with some example references that NEXO has. And the second part of that webinar is going to be a practical exercise on NS1, and I will show you quickly, in reality, how how we can manage a 20,000 seat arena and design for such arena from the default page of NS1 in reality, which features this arena. Another quick word also, you have a chat session that you can use. See, I can see some messages here, and Bertrand went already too fast, but yes, please use the chat session to say hello or to put your comments and so on. But if you have questions, use the Q&A parts, which Garrett and Reinhard are going to monitor. And I can see here people chatting on the Q&A session. Hey, Bert, how are you? So this
Morning,
is not
Bert.
a question. Good morning is not a question. But anyway, welcome everybody. And I think this is it. So I can start. We'll take, did I say we will take a short break, maybe 10, 15 minutes at the end of the PowerPoint, so that everybody can have a quick coffee or espresso before we carry on with the models. So let me now share my screen, and I will start with this PowerPoint here. And there we are. So sports arena and stadium sound design. Let me make a quick word of introduction on the story of NEXO with stadiums and sports arenas. It's in reality, and this in fact connects me very much to my story with NEXO because I was a consultant at that time. But NEXO is a company doing, speakers for live shows, entertainment, theaters, opera houses. 20, 30 years ago, we were not really involved 30 years ago into this kind of venues. Reason for that is that most of the sound system 30 years ago in sports arenas were systems for safety, with very limited bandwidth for speech only and so on. And there's been a trend so that sports arena would in fact improve their sound systems as well as their video display and so on, so that they really become more entertainment for the audience and just can have enjoy a nice experience and nice emotions there. And what triggered that for NEXO is in '96 we were competing for the Stade de France installation. That was the Soccer World Cup in '98. And so, in fact, we submitted a project with NEXO, and it turned out that we won. That project was with Alpha System. It was a full range system, and it was a loud system because there were already some concerns at that time about safety. So when you have to deliver 105 dBA from 50-meter height, the conventional, horn speakers that were available at that time on the market could not make it. So it had to be professional live reinforcement systems. So we won that. We installed at that time something like 300 alphas. And again, it was a full range. And it gave us a great deal, I believe, of know-how, because not only we designed, but we've been monitoring, following very closely the installation all the way down to the commissioning. And it turned out that it was at that time the biggest sound system ever installed in Europe, and that it sounded superb and everybody complimented it. So that, in reality, of course, generated a great reference for NEXO. It is still today, I will go over it, a great reference. And it generated, of course, many, many other projects, which we will see. So I'm going to cover a little bit of some of the late references we've been doing. This is not comprehensive, but you can see, in fact, how wide is this domain of a sports arena and stadiums. Here is the Stade de France, as you can see from the top. And by the way, the Stade de France, which hosted the World Cup in '98, is going also to host the opening and closing ceremonies of the Olympics in 2024, which are going to occur in Paris. So you can see here a quick picture. And what you see here is not Alpha, it's GOS 12, because in 2010, the sound system was replaced. So we went through a competition again, and we won again. So we have now 280 S12 systems, together with the RS18 subwoofers. I will talk about that. The Stade de France is the first stadium we did with subwoofers. When I say that the trend is improving and improving the experience, the audience experience, subwoofers are widely becoming part of that. And so it's a real full range system down to 25 Hertz. So this is Stade de France. Garrett and Reinhard, don't hesitate to interrupt me whenever you want to. Garrett, you were part of that project. This is in Ireland, in Dublin. This is a Croke Park. Yep.
The third largest stadium in Europe.
Third largest stadium in Europe. It's, I think, 90,000 seating capacity, if I am correct.
Crack under, yeah.
Yeah, so also done with S12 that was completed 3 years ago.
Yeah.
And yes. And a picture which is interesting here, it's the same Croke Park Stadium. And in fact, 1 month after we commissioned the installation there in June 2017, in July, the Pope was visiting Ireland. And so, as you can see, they used the pitch to put lots of seating here. And we also provided all the STM system, thanks to John Vickers in Ireland. And so we installed, I forgot how many, but around 200 STM systems, as you can see here, as main PA and delay PAs, also using the S12 combined with the S12 systems. So that was a nice event, and it shows a little bit of the wide range of applications Sports Arena can cover. This is one of the latest success we had. It's the Etihad Stadium. It's the stadium of Manchester City Football Club. So, you know, very successful, of course, football club, soccer club in the UK Championship and the European Championship. This is the SketchUp model, as you can see, and this is the installation that was commissioned something like a year ago, I believe.
Yeah, about 12 months. Yeah.
12 months ago. And again, it is S12 being installed here. This is one of the latest. It's in Japan. It's the Toyota Stadium in Japan. Again, S12. And Toyota Stadium was used for the opening and closing ceremonies of the Rugby World Cup last year. So that was July 2019, if I am correct. And so again, it was to be used, is to be used for the Olympics, although the Olympics of 2020 have now been postponed to 2021. You see a beautiful stadium, very challenging in terms of environment because of the closing roof. So we have to deal with two different acoustics. Anyway, that's something totally different. This is a baseball. It's the Nagoya Dome in Japan. So it's a baseball stadium. It's again with S12, which in fact we don't see on that picture because they're on the top edge of the picture. But these are S12 clusters who are at the center of the venue. All right. In US, we have also very nice references. This is the University of Cincinnati in Ohio. And you can see here, it's a multi-purpose venue, which is used for tennis, for basketball. And you can see the design here in NS1. And it comprises STM M28 clusters together with cardioid subwoofers implemented the way you see them. And you can see also additional clusters being installed for the pitch coverage. Angel Stadium of Anaheim in California. This is also an STM M28 installation. It's one where we had to go really fast. It was a bit challenging because they asked for custom color STM M28 of a specific green, so it's baseball again. And I think we were capable to produce them in 2 weeks, which was quite a challenge in terms of delivery. But anyway, and this is, you see, it's a challenging stadium also because the sound is coming from the back. The roof is not covering the seating area, and like it occurs most of the time in Europe. In US, very often the stadiums are open, so we have to shoot from the back, and this is a topic I will cover also later on in that presentation. Ice hockey arena. This is a Place Bell Arena in Laval in Quebec in Canada, and you can see again S12 clusters being installed everywhere together with the LS18 subwoofers. So it is a full range system. They are distributed among the stands. And you can see here the design with the subwoofers, and you can see the kind of coverage we achieve. We manage in these venues usually because of S12 and because of M12. We manage to do design where the direct sound coverage falls within plus minus 2 dB, plus minus 1.5 dB. This is what we're aiming at. And this is usually, we achieve usually, a much more consistent coverage than what is usually required, which can be plus minus 3, plus minus 4. A very nice reference we're very proud of also. This is the Optus Stadium in Perth in Australia. And this was completed in 2016, if I remember well. And it is a 200 S12 together with a LS18 subwoofers. Very nice project, beautiful project, as you can see. It's very significant of also how the sports arenas are progressing in terms of architectural design. And the way these arenas are designed today is just unbelievable. If you look at the stadiums being built today in US, in Europe, they are really architectural masterpieces. This is important for us because it means that when we step in with speakers, we should have something good looking, not ugly. And so you can see here, this is the inside of the stadium, and you can see the clusters. I think the next picture shows a more detailed cluster, and you can see here. So we have, these clusters are 12 S12 every time, plus 3 LS18 subwoofer, all in a special housing. Special housing because the wind velocities that were to be taken into account in this open stadium, you can see it's open not only at the top, but it's also open below the roof above the stands. So wind velocities can be very high, and this requires specific custom design rigging hardware. And here is, how we do the designs, and I will illustrate that later on anyway. But you see, it's because GOS 12 can vary in angles from 0 to 30 degrees that we are capable to achieve constant coverage without shading any signal. We don't have to lower one box in respect to another. We send the same feed to all the cabinets. We parallel them 4x4. So it means that on one NXM 4x4, a cluster like this is only using 3 channels. And I deliver, as you can see, a very consistent coverage. And I go now 3D, and you can see this is the coverage we achieved at direct sound at Perth. So these are a couple of the references, and I must say that at NEXO, again, we have a very good experience, willing to share that experience with the people who are asking for support. We probably have, I would say, 1 or 2 projects per week. I'm not saying we win all of them, but we submit them for sure. And in fact, before that session, I was working with Carole Marceau, head of installation at NEXO, on the sports arena that were being submitted. So let's look at what is...
Francois, can I just jump in there for a sec? The only thing I will say as well is that we do an awful lot of smaller sports venues, which are outdoor venues as well. So when you're looking at the NEXO references and you're seeing big clusters of GOS 12 in very prestigious venues, you've got to remember that we have lots of venues, much smaller, also successfully using a more cost-effective NEXO solution. So even down to Wolves Football Club in the UK and their Molineux Stadium, where the entire stadium is running on PS10s and PS15s. And varying single stands in a lot of UK football clubs using PS and PC and now Plus series as solutions. So yeah, don't get put off by big clusters of GOS 12s. We do little ones as well, just as cost effectively and just as well.
You're absolutely right, Garrett, because a sports arena can be from 4,000. It can be a gymnasium, for being used for basketball. A recent example also that I did not show in this picture, which is an architectural masterpiece again, is the arena of Aix-en-Provence. It's a 6,000 seat capacity, and we've been installing there 36 GOS 12. So they run on, I think, 2 NXMs or maybe 3 at the maximum. And we deliver 104 dBA over 6,000 people with 36 GOS 12. So yes, it is a very good point. But P series, the Plus series plus the GOM series plus GOS 12, they allow us to go from sports arena venues, which are 3,000 all the way to 100,000. And we always have the right solution, I believe. So let's go a little bit backwards and let's think a little bit what are the reasons for sound in sports arenas? We need sound in sports arenas, first, because sound is being used the same way video is being used to manage crowd. Manage crowd means that in case of an incident, the sound system as well as the video are going to be used to deliver the messages and to manage the crowd movements. So in that case, in that picture here, we can see a storm coming in. So people have to go, to their vehicles and exit the stadium. It can be all sorts of problem. It can be fire. It can be a terrorist attack, which occurred unfortunately in France back in 2015. So for all these reasons, it means that the sound system there is there to protect people's life. And this is very, very important. We're a level, I should say, above entertaining. It's first protect people's life. So it's a serious matter. Maybe the examples I'm going to take here are a little bit focused on soccer because this is very much a very popular sport. You should know that how sound is being used in sports arenas depends very much if it is basketball, handball, rugby, NFL, soccer in Europe. Each league, each organization, FIFA, Euro League, NFL, they all have the rules of how sound should be used. But so let's look a little bit in the case of soccer, for example. Well, when it's a World Cup, the players, sorry, are becoming singers. They have to sing the national anthem, and we have to play the national anthem of all the teams which are there. There was, in fact, at the last World Cup, a little bit of emotion because I believe that in one of the games there was a confusion on the anthem, and the one being played was not the one of the country who was, on the field. So you see, it's important. You better have the right tracks at that time, and you better have them sounding good. Again, in the soccer case, sound is not being used that much. It is used at the half game, you say, Gareth? Yes.
Yep, halftime. Yep.
Halftime. Sorry, for commercials and so on. During the game, it is used during interruptions. Interruptions are about goal, so we need to know who has been putting the goal, and it's also used for replacement. We need to use, the game is interrupted, there is a replacement, and we must know who is going away and who is going in, and this is done with video and sound. All right. And of course, the sound system is also used before the game with music to entertain people and so on.
Francois, if I may, just a quick one on that. When we first started working on Manchester City the first time, the marketing department there were very, very solid in their message that the sound system was about delivering a fan experience. What they wanted to do was stop the fans looking down on their mobile phones and texting their friends, and they wanted the fans to look up to the video screens and experience the day.
Yeah.
Which is a great thought, but in commercial terms, this is all about clubs making more money.
It is.
As you're coming to now with this slide,
yeah.
It's about monetizing the fan experience inside the venue.
Clearly. When you look at Gareth, when you look at how the video screens quality has been improving, over the last 20 years, resolution and so on, and when you look at where they are today, it's very clear that when you have such beautiful screens, the sound must be also, to the level of that. It cannot be. And yes, Gareth, to illustrate what you're saying here, yes, these arenas, eventually they have naming contracts with partners, and they're going to play commercials, and this is going to generate income. I can give you a simple example, Gareth, to illustrate what you're saying. Back in 2002 or 2003 at the Stade de France, again, they had an outdoor system to the outside perimeter of the stadium. And the sound system there, which was not NEXO, was just ruined, falling apart. It just couldn't do the job. And so the people that were the customers playing commercials stopped playing commercials because nobody could hear the sound. And I can tell you, it took 3 months only before the sound system was entirely replaced by a decent one that could be intelligible for all the commercials. So yes, it is part of a strong part of the income, of course. That's a bit specific. Maybe it's a bit new, but it's about acoustic enhancement. It's about crowd enhancement. You should know that there is a contradictory requirement for sound in sports arenas. There is the fan experience, as Gareth mentioned. The fan experience requires that the acoustic is very live, so that when they applaud, right, they really feel encouraged and they say, wow, this is great ambience, and they want to hear the crowd and they want to be part of the crowd. This is the fan experience. So this requires very live acoustics. However, it contradicts live acoustics with intelligible messages in the sound system. Intelligible message in the sound system requires a low reverberation time. So this contradiction is difficult to manage. And we already have now at NEXO over the last year, we've done 3 cases of a stadium, Headingley in UK, that was, I believe, very first. And then Qatar University also we did in Qatar, where in fact what we do is we dump the acoustics to a low value so that the sound from the PA sounds really good. And we put many speakers to enhance the acoustic over the crowd. So when people are, when the PA is not playing, people feel they're in a very live environment. And when the PA is playing, then we shut down the acoustic enhancement system, and suddenly it's very intelligible. So we have we're starting to have a couple of nice references here. This is based on the Yamaha system. Yamaha pioneered on an acoustic enhancement system. They have a system which is named AFC4. So anyway, this is not the main topic of this presentation, but AFC4 has been launched last year, but it is, I believe, 30 years now that Yamaha is involved in acoustic enhancement system. So this is also a trend, so that we can manage these contradictory requirements for sound systems in arenas. For that reason here, you can see this is a tour occurring, and that it's a festival. In fact, it's a hip hop festival, sorry, that one. And you can see the crowd on the pitch. So no, we don't need a sound system to, in the stadium, a permanently installed sound system to do concerts. Reason for that is that these sound systems are coming with the artist or with the production of the festivals. So the design is always different because the design is related to the requirement of the tour or to the requirement of the festival. So no, a sports arena should not invest in a concert system because this is not going to be used for that specific case. But maybe I can put one or two points here. Clearly, I think that a sound system in sports arenas today should be capable to do all the ceremonies, all the events, which are sports events or specific events or corporate events. But for sure, they will not do, the concerts, or they will not even be used in complement of a concert system on the tour. Point number one. However, I think I have that on the next slide. No, I'll use the same slide. On the Y, you have this audience on the pitch, on the field, and so you need to be capable to talk to these people in case there's an incident again, if you have to manage that crowd. So we should never forget when we do designs that sound is not only for the stands, because if it is anticipated there's going to be audience on the pitch, then we need sound for the pitch for crowd management.
I just throw in a very quick example there. In a previous life with a previous manufacturer, we installed the O2 Arena in London. And on the opening night, which was for all of the staff for the biggest sponsor, which was O2 Telecoms, Tom Jones was live on stage with a full concert system, full production, nearly 20,000 people in the audience, all hand-picked. Halfway through, there was an announcement for somebody would move their car, which absolutely destroyed the concert system. And that was the system we had installed as the PAVA system. And it was actually louder than the concert system that was playing to all those people in that audience.
Yeah.
So in the middle of Tom Jones's set, everybody was asked to leave the building to move their cars. So yeah, prime example of how loud it needs to be.
Yeah, should never forget about that. Very important. So when we design, when we're submitting a design at NEXO, we have some requirements of information we must have. Usually, we have the CAD files for cross sections, top sections. Eventually, this is great. We can have SketchUp 3D files. So that, but let's look at what we really need. What are the hypotheses we need, so that we can after that commit. We need reverberation time hypothesis. This is very important. Usually, it depends on the size of the venue, but reverberation time can range from 1 second if it is very, very much damped, to 1.5 seconds, but it can go up to 4 or 5 seconds eventually in very large arenas. So we need that information, because if at some moment the reverberation is too high, then we cannot commit on our side on the result, and more specifically on intelligibility. This is very critical. So again, when we install a sound system, there is a threshold below which we will not go. And if reverberation is too high, it occurred, as you know, Garrett, a couple of times, we will not go, simply because we know that in such acoustic environment, the sound system cannot make it, whatever is the sound system, to be very honest.
Then we cannot commit on our side.
So this is reverberation time hypothesis that we need. Second, this is background noise. I'm sorry, that picture is a bit humoristic, and this is a French president during the last World Cup. It was France, Russia.
I get sad overexcited.
Yeah. Putin is not very far. You can see Putin sitting here, and you can see Macron here, stepping it on the table. But anyway, what this slide says is that the crowd noise can be extremely high. So the ambience in the stadium can be very high. If the ambience of the stadium is evaluated, I'm taking a simple example, at 90 dB, and the system is delivering 92 dB, then the sound system cannot be intelligible very clearly. So background noise is needed so that we know how loud has the sound system must be, right? To give you some numbers, FIFA did some measurements in finals of World Cup, and they found that over an entire game, that is an hour and a half, the two half times, the average background noise is around 86 dBA, right? So this is L equivalence measurement over 90 minutes. At 96 dBA, you should know that intelligibility becomes, STI measurement becomes independent of background noise. As soon as we are above, we're capable to go 15 dB above. So this means 186 plus 15, this means 101. And this would be also an equivalent level. So in reality, probably we need additional 6 dB headroom if we want to be really sure. So you see where this takes us. We're going in the range of 102, 108 dBA. This is usually the requirements and the designs we do. If we're being asked to do a voice evacuation system at 96 dBA, we will not go, because we know that such system cannot do the job. Okay, and I'm taking here an extreme example because these venues are being used for many different purposes. This is the loudest event I ever heard in a stadium. It's monster trucks, and they're so loud. And they're so loud, and the announcers and the speakers have to go above that. It's so loud that it gives you headache. But anyway, realistic, this is not very realistic hypothesis. It maybe occurs once every year in the stadium or once every 2 years. But anyway, this is an extreme case I wanted to share. Also, it is very much the case, especially in dense areas such as Europe, but very often stadiums being constructed are part of a urbanistic plan. They want to dynamize the whole area. For example, the Olympics in Paris, which are construction is starting now. This is north of Paris. And so they're putting many swimming pools, stadiums, arenas. And the purpose for that is that this whole area will be constructed, with buildings afterwards. And this is going to value a lot, that whole area. This is very often the purpose of World Cups or Olympics. This is the Maracanã in Brazil. When the Maracanã was built in the 50s, there was no one around the Maracanã. And you can see now it's in the middle of a very dense area. This means that we have to take into account the sound generated from the stadium to the outdoor and to the outside environment. So we have to also evaluate that. Usually regulations in Europe, they slightly differ, but they specify that from the background noise of the environment, which can be, cars, which could be during the day, the increase of level due to the stadium activity should not be more than 5 dB. And from 10 o'clock in the evening, it should not be more than 3 dB. So you see, it's a bit of a challenge because we're being asked to deliver 105 dB A inside, and we're being asked to deliver, 65 dB A outside. So that's not an easy one, but we have to look at these figures and we have to make hypotheses there, of course, as well. So then next question is, what are we going to specify? So we're going to specify, I take this example, okay, this is a sports arena. It's a 0.55 and we want at least 105 dBA. And you see, we want sound pressure levels in a range of 7 dB. This is plus minus 3.5. And you can clearly see from these specifications, you can clearly see that frequency response is being should be 120 to 5 kilohertz plus minus 3. So this is clearly a speech sound system, right? If we play music in such sound system, it's not going to sound really good with such a limited bandwidth. So anyway, we have a maximum SPL which is being specified. Intelligibility, I would call intelligibility as the minimum criteria. Intelligibility is what is specified is usually the speech transmission index. To make it very simple, we usually consider that below 0.5 is not good and above 0.5 is good. There are different regulations. NFPA 72 in US, I believe, specifies 0.45 minimum. But anyway, it's good to be not to be below that. 0.5 is usually the point we take. At NEXO, we always build our models with empty stadiums. So we take the worst acoustic hypothesis, and we want to be sure that within these worst acoustic conditions, we achieve proper intelligibility. If the stadium, which is 20,000 capacity, if you only have 3,000 people, the acoustic has not changed. You still need to be intelligible for these 3,000 people. So always, again, working on worst case scenarios, so we only get good surprises. This is fundamental. And the plot to the left shows a little bit mechanism of intelligibility. Intelligibility is about consonants and vowels. The consonants, sorry, Garrett, consonants are the elements that give us intelligibility. What are consonants? Consonants are P, S, T, Q. These are consonants. And you can hear as I talk, these are transients, right? They are transients, and so they have a very rich content in the mid and high frequencies. While the vowels, A, A, O, U, you can see are low frequency, right? And again, keep in mind, intelligibility is not given by the vowels, but is given by the consonants. So it means that when I have a reverberant field, these transients have to emerge from the reverberant field. If the transients are above the reverberant field, then I have intelligibility. And this is what you see on the second plot, bottom right. But if the consonants are not emerging from intelligibility, this is the bottom plot, okay, then I lose the meaning of what is being said, right? And in fact, one of the criteria which is quite often used also by acousticians is called percentage of articulation loss on consonants, alcons. Percentage of articulation loss on consonants, the threshold is set at 11.5%. It means, in a concrete way, that if I lose more than 11.5% of the consonants, I'm not capable to reconstitute the meaning of the word. I lose the meaning. That's very important. So you see, it's about transients. And when I'm saying that intelligibility is the minimum we have to achieve, it means that if I'm playing music, music is also about transients. Very much. The content of music is transient. The sound is good in any place, in a live venue, in a concert, because my sound PA is respectful of these transients. And if these transients are not properly reproduced, the sound quality is poor, right? So again, when we design at NEXO, because our job is music, we design for the full spectrum. We do not design only for 125 kilohertz. We design for the full spectrum, and we design for great music, audio quality, not only speech. If we have great sound system with great music, I can bet you it's going to be intelligible, no problem. All right, and this is to illustrate. You can see here, this is typically the frequency responses we're looking at when we go in such arenas. And you can see the bottom end, the main cabinet is in black. It goes down to 60, 50 hertz, something like this, 60 hertz, which is quite low already. Yeah? This is going to be a Geo M10, for example, in our catalog. But the bottom octave, the last octave, the one that goes from 25 to 50 or 60. This one is extremely important in the way we perceive subjectively the audio quality of the sound system. If you go in a stadium and there are subwoofers and that octave is there, you're really going to go, wow, you know, this is great. I'm not used in a sports arena to have this kind of, you know, people say, wow, it's like in a home theater. You know, they feel that there is exactly like in a movie theater, you have this, you know, VLF component below the screen. It is the same there. It really gives a perception of sound, which is great anyway. And I'm sure that all of you, especially during the lockdown when we watch movies at home, you know, yesterday I was watching a movie with my kids, and the low frequency content, the very low frequency content is so important, you know, so that we are immersed into the sound. This is an example, and you can see the LS18s being integrated into an S12 cluster here. And then we have to look at coverage. So we look at coverage when we design. We have to optimize direct sound coverage. This is very important. We don't know yet about the reverberation, what it's going to be, but reverberation is a little bit like a capacitor that gets loaded and unloaded and loaded and unloaded, right? And usually, this is, I'm taking some precautions here, but it is assumed that a reverberation field is more or less constant throughout the audience. So if I want to have a constant direct to reverberant ratio everywhere, my job is to have constant direct sound. If I don't have constant direct sound, it means that the D to R ratio is going to be extremely high in some places and very low in some other places. So I can achieve great intelligibility in some seating areas and very poor ones in some other. And I cannot accept that. I have to fight so that intelligibility, D to R ratio, is as narrow as possible in terms of distribution. So this is, again, you see, when we design, we usually design at less than plus minus 3. Okay, and pitch coverage, I mentioned that about, in fact, I'm repeating myself, but yes, pitch coverage. We usually, if a stadium is, if a sports arena is specified at 105 dBA, we usually don't look at the same values for the pitch because this would be too many speakers. This would be twice the same quantity of speakers for, you know, very few events. So there is a little bit of an economic thinking behind that. What we usually look at is pitch coverage being 10 dB below. So if we aim at 96 on the stand, we're going to look at 96 on the pitch, and the sound system will be used separately, which is if I want to talk to the audience on the pitch, I'm only going to use the pitch clusters, okay? So I can segregate the messages from the pitch to the stand. There is something also that is not shown in color maps, as we've seen just before. A very important criteria for the experience is sound localization. And sound localization, when I work in a live venue and I do a concert and the stage is here, I don't want the sound to come from the ceiling. I want the sound to be coherent with the stage. The same occurs in a sports arena. I can have a great coverage with plus minus 1.5 dB, but if the sound comes from the back, it's a bit annoying because in reality, if there is what we call the cone of attention, hearing cone of attention, this is more or less 120 degrees, right? And this is where we expect the sound to come from. If someone talks to me on, you know, to my left side, I'm going to move my head to look at this person talking. So it's the same with speakers. If we manage to use central location rather than distributed, and you can see here, this is in Prague. It's the O2 Arena in Prague, and we're using clusters around the scoreboard. This is really nice because it means that people are sitting and they have some level of coherency between the sound system and what's occurring on the field and the event itself. So speaker location is quite an important criteria. There is something which is rarely specified. I see from time to time, we see IP rating for speakers, you know, IP54, IP55. I'm sorry to say that IP rating is not relevant at the time we want to specify weather resistance for speakers. IP rating is about electrical parts protections to dust and to water, right? But it definitely does not tell you how long the cabinet is going to last. So it doesn't tell you about the weather resistance. You can see here, this is a small stadium that we've done north of NEXO in Beauvais. It's GOM10 being used. And you can see GOM10, the GOM range is made of a composite based on polyurethane. And weather resistance is, of course, extremely strong, absolutely no problem. And so is resistance to ultraviolet, so sunlight, that's also very important. So in outdoor installation, we have to be very cautious at the time we start using wood cabinets. Even though we use special coating, the resistance is not going to be that much. So specifying weather resistance is a little bit more like looking into marine standards. Another thing we have to look at are wind loads. We have maybe once every 5 years, once every 10 years, extreme winds in one location. Okay, so winds can go eventually up to 150, 200 kilometers per hour. Well, even if it's only one day, I must be sure that my rigging system can resist to that. So we have a TÜV certification at NEXO, which is based on the maximum winds of 72 kilometers per hour. The focus there is very much live events. It means that if winds exceed 72 kilometers per hour, the system should be taken down. Okay, if our systems are to be exposed to higher winds, such as the Stade de France or Perth in Australia, then we have to design a custom rigging system that resists to such wind velocities. This is very, very important. And keep in mind that wind velocities to be taken into account are regional. They're not even national. They're regional. It means that in France, for example, the wind velocities that we have to take into account in a stadium in Beauvais are much lower than the wind velocities that we have to take south of France, for example, in Marseille, where high winds are extremely common. So these are the things. Of course, we need to have a monitoring system because in these places are big. We cannot expect the sound engineers to go and check all the racks all the time. So we need a very good monitoring system, which can be custom designed, such as in the picture I'm showing here, so that the engineer, when he steps in 1 hour or 2 hours before the show, he can control that everything is working properly. This can be done today on a custom basis with NEMO. NEMO is the remote control solution of NEXO. And we have a custom page where we can monitor and put a couple of controls, and this will allow, quickly to build up a monitoring system. When I'm saying monitoring, it's about amplifier properly working, it's about speaker impedance, it's about signal continuity, all the way down to the amplifier, from the amplifier to the speakers. It's the fans, it's the power voltage, it's the power supply behavior. These are all the elements, the speaker displacement, the speaker protections. These are all the elements we can use and we can monitor in NEMO to check how the system is working. Redundancy, this is very important, especially at the time the system are being used for safety, but not only. Redundancy is about risk assessment. When I'm designing a sound system for an arena, I have to look at the components, all the components one by one, and I have to evaluate the consequences of that component failing, right? If I have an amplifier which is feeding 4 under balcony speakers and that amplifier fails, this is not, I don't consider that as critical. If I have a switch which is managing all the amplifiers of the entire sound system, this is very critical, of course. And of course, I'm going to do, if I use Dante, I'm going to go in redundancy mode. So I'm going to use, in fact, 2 networks in case one fails. If it is, if I'm not working on redundant mode, I can also back up with analog. So I can have signal feedings analog, and I can have the digital network, and we have that mode. If the network fails, then it falls onto the analog. So this is another way of assessing the failure. If I have an NXM 4x4, like we can see in these pictures, I mentioned that the 4x4 can feed up to 4 S12 per channel. That's a total of 16 S12 per channel. 16 S12, let's say each S12 is 300 people, that's 5,000 people. So one amplifier failing is up to 5,000 people not being delivered sound. That's not acceptable, okay, not acceptable for safety and not acceptable for entertainment. So we have at NEXO this backup system, which is very common in 70 volts or 100 volts amplifier systems. And this is so that if one amplifier fails, there's a backup amplifier that can take over in a transparent way. So thanks to the DPU, which are output relay boxes of high power, high voltage, we can back up 25 kilowatts of power on our amplifiers. So I can have a rack of 5 units and a 6th amplifier. And if one of the 5 amplifier fails, it will automatically back up on the 6th amplifier. All right. I believe, to be confirmed, but I believe we're the only company providing that feature at low impedance, high power feature. And then also we have to look a little bit outside specifications. These things are difficult to specify, although they can in reality. Speaker elocution. I can install a great sound system, but how the speaker is going to talk in his microphone, right, is fundamental to how the audience is going to perceive the sound. If he talks very fast, not taking into account that there is 4 seconds reverberation, that there is ambience, there is crowd, that's going to be difficult. It's going to be a pain. People are going to have to really concentrate to really understand what he's saying. It's annoying. Now, if the speaker is talking properly, with some interaction with the crowd, putting his voice in a dynamic way, and a nice low vocal like this, a Russell Crowe of the speakers, this is going to be great. And this is of course difficult to specify. However, there is a new British standards that came out last end of the year 2019, which I encourage you to look. I will check the reference and give it to you. And it is about design specifications. It's a very nice piece of document, and it specifies training for speakers. Speakers should be trained to sound systems. When they go in arenas, when they go, this is very important. It's maybe a half-a-day training, but this is very important. This is going to be very helpful, including for them and for their job, because this is not being in a radio studio. This is about being in a very live environment. Theatrical comedians, they know that by heart, of course.
If I can jump in there, Francois.
Of course.
With reference to the British standard that you're listing there, it actually states that speakers should be educated in the correct way of speaking, but it doesn't actually define the training. There are, if you go to, and the website's open to anybody that wants to look, but there are industry organizations now, I think Avixa in the States are working on speaker training. And certainly for the European market, the Institute of Sound and Communications Engineers in the UK are in the process of finishing off a degree. Well, it's not quite a degree level, but it is a course that will, for speaker training, which is not only aimed at this market, but also, for instance, public transport announcements over microphones for public transport and things like that. So that is an accredited training scheme that's currently being set up in the UK, specifically for speaker training in this environment for safety. So, and between Avixa and the ISCE, this is going to become a big push in training worldwide, I think, over the next 2-3 years.
This is great. This is great, Gareth. And in reality, as soon as you have the reference for these trainings, give them to me, and I will include them into these presentations, because this is really key. I would love to be part, in fact, of one of these training sessions.
I will arrange to introduce you to the man that is writing the course.
I heard so many different things. I heard the best and I heard the worst. And I'm happy you talk about public transports, because in our French fast trains, when they make announcement, it's not announcement, it's just feedback, because they don't even know that the microphone should be far from the speaker. You go in your train and you get all these feedbacks in the entire train. It's very unpleasant.
Yeah,
anyway,
it is.
Yeah. So it is also about microphone handling and all these kind of things. Again, all these things that musicians and comedians know really well.
Yeah.
And last, outside specifications is, of course, the skills of the audio engineer. When we're operating a sound system for a large amount of people, from 3,000, 6,000, 10,000, whatever, you know, the man at the console must be a professional. It cannot be the electrician, or it cannot be, you know, I don't know. It has to be someone that really knows about sound. And more specifically, I'll tell you why. In most of these venues, unfortunately, the control rooms are behind glass windows, and these glass windows will not necessarily open. Many times they're closed. So the sound engineer is mixing on a pair of monitor, not knowing, not having a clue of how it's sounding, in fact, outside. So he has to make this permanent effort, right, of interpreting what's coming into the monitors and having the right how would you say, connection with what's occurring outside. If it is a freelance who comes there for very first time, it's going to be very challenging for him. The people who go there, they must know the arena, they must be experienced because of that specific problem that I'm mentioning. So never underestimate the skills that are required to operate a sound system in a sports arena. And outside specifications, again, I think I've put last 2 times, and it should be, there's only last one. Aesthetic integration. We mentioned, you can see this is the Dalian Stadium in China. And of course, this is a beautiful roof, you can see. And our design had to be so that we would be above these transparent panels which are in the ceiling, so that we would not see the speakers. What we would design again 20, 30 years ago in terms of clusters in stadiums would not be accepted by architects today, and this is quite, I believe, normal when you look at what they do and what they design. I'm going to take a very quick example. I'm being a bit, I'm running a bit short of time, but that's okay if everybody's still here with us. The way we design, and I'm going to do it shortly after the break, but you see, this is Stade de France design in 2010. A first cluster to cover mid and upper stands, adjusting the angles properly so that we get constant coverage. We then introduce a second cluster, and this is for the lower stands again, and we check you know, how the angles should be splayed so that we have the same level. We then implement these 2 clusters in a stadium, as you can see here, and I have the idea of the horizontal coverage. And I know that the steps between the clusters, my next cluster should be somewhere between the -3 and the -6 dB area. So I know what's the horizontal spacing I have to put. To be honest, very often the horizontal spacing is not only governed by the coverage, but is also governed by the steel structure that I have in the roof, which imposes eventually some positions. And I'm going to duplicate these clusters all around, you see? That's a difficult one because, as you can see, the upper stand height is varying depending on the southwest, northeast. I would say that probably 60 or 70% of the times, the cross section of the arena is constant. So in fact, I can take one cluster and I can duplicate all around, and it's going to give the same result. So you see here, again, ±2 dB, and this is without the pitch. I put in the reverberation time. I use ease to check that. So you can see reverberation time, 4.3 seconds. And then I look at direct sound in ease, which in fact is the same than in NS1 because it is the same algorithm computational algorithm. Then I put reverberant field on top of it, and you can see it smooth out a little bit, the response. And this is normal because the reverberation is smoothing out. It's not a very good sign when it's smooth too much. If I see a perfectly constant level all around, I say, yeah, look at my coverage, it's great. No, it's not true, it's not good. It means that the sound is totally drawn into reverberation, and this is not good. And then we evaluate intelligibility, and you can see here, this is the intelligibility distribution with an average value which is around 0.6, with a maximum at 0.7. And the lower values, as you can see, are on the corners over there at the top. And this is because I have clusters. It's very difficult with these clusters to go into the corners and not hit the glass window, which is actually facing the same cluster. So there is always, I didn't mention that, but when intelligibility is specified, it's usually like 0.55 over 95% of the audience area. This is typically specifications we usually receive. All right. A last one, because we often have the question, you know, should we have 2 sound systems or should we have 1 only? Well, that table shows to the left what are the requirements of a safety sound system, and to the right, it shows the requirements for an entertainment sound system. And you can see that in reality, the requirements for an entertainment sound system are much higher than for safety. So it's a case-by-case situation. This is very much related to EN54 in Europe. But anyway, whenever you want to discuss about 1 or 2 sound system, feel very free to come and knock at our door. We'll be happy to discuss with you about that. And please note this one. Probably Reinhard or Garrett should put it on the chat section so that attendees can copy and paste. But anyway, technical@nexo.fr. This is our mail address for engineering support. It's 10 people permanently connected worldwide. Any question, any information you need, any support you need for whatever that involves NEXO solutions and systems, feel free to contact us. We'll reply to you very quickly. And second, below is a link to our technical cloud. On that link, you can find all documentation of NEXO. You will find all the EASE files, NS1, software, NEMO. You will find everything that exists in terms of technical information at NEXO is on that cloud. If you don't find it there, there are high chances that in fact we don't have it, and maybe we'll have to generate it.
Francois, we've got one question before we move on to the next session. Our friend Bert
yes.
Has asked, how does the DPU technically work with the backup amp?
This is also a point I have. We do it software-wise, and the hardware we use for it is the DPU. Very important to say that the DPU has a double power supply and is acting inside also redundancy. Huh?
Yes, DPU has 2 sets of 64 relays and 2 power supplies, operates 70 to 40 volts. And it communicates with NXM through the GPIO port, okay? And so there is a technical note which is available on our cloud, Bert, which tells how the system should be wired, all right? And the thing is that on the GPIO port, the DPUs are going to receive the information that this amplifier has a global failure. So it can be power, it can be whatever. But this amplifier has a global failure, so it's a synthesized information. And from that, it decides to toggle, right, to the last amplifier, which is connected. So if you want to look at that technical note, or if it's not there, then of course I can share it with you, absolutely, no problem. We have a couple of arenas. The first one we did is the O2 arena in Prague with such system. And we have now many more, because this is of course a key feature. You don't want again to have 32 or 16 speakers failing at once. So I hope this answered to your question. So it's 11:04. May I suggest we take a 10-minute break and we restart at 11:15?
Okay.
For all of you?
Fine.
And I will restart
yes,
with an NS1 example.
Cool. See you in 10 minutes.
See you in 10 minutes then. All right. So welcome back. For the questions, we're all fine, I believe.
Yeah, nothing outstanding currently.
Nothing else then. Anyway, we'll keep, of course, we'll reserve a little bit of time at the end of the session for question and answers if you wish. What I'm going to do now, I'm going to do something extremely simple. I'm going to take an arena, which is around, I believe, 20,000 seat capacity. It's a real example. And I'm going to illustrate how we do the designs in NS1. So let me share the screen. I'll share my NS1 page here. Again, NS1 is available in the technical cloud link that we gave you. So in fact, the model you can see here is the default model that you have when you open NS1, right? So you see, I have no speakers here. And I'm going to do quickly the project. I assume that, again, we're aiming at, sorry, let me move these so that I can, all right, and let me go to GOM. I'm going to do a project with GOM 12, for example. And what I'm going to do very simply is I'm going to drag and drop, okay, a cluster. I don't know where it is, it doesn't matter. I'm going to set the height at the same value, in fact, that the upper stands, I believe, something like this, or the roof, sorry. And I go okay, and you can see my cluster here is at the center, which is not the proper location. And if I want to move the cluster, and I assume I'm going to put it somewhere here. So you see, on this plane view that I've inserted, I can see the beams, right, of the roof structure. So of course, I'm going ideally to position, my cluster along a beam. So let me put it here, and of course, let me rotate it to the audience. Okay, so somewhere around this, and it should be going flat this way. Oops, okay. I double click here. I just tune the angles. The angle should be 90 degrees. And now 90, I said up, okay. And now I go on the speaker view here, and you can see this is my cluster. So I can design, this is something a little bit unique at NEXO, should I say, if I may. But all our GOM cabinets and GOS 12, in fact, we have, it's one box in reality, but it's two models. It's, we have, in the case of M12, we have a box that ranges from 0 to 10 degree, and then we have a second box that ranges from 13 to 20 degree. So to show you quickly, let's start with simply, let's imagine I only have the 1210. So I only have a 10 degree cabinet. Well, I'm going, line arrays are very simple. I don't want to demystify the whole story. However, line arrays is two sentences. I want to increase the level in one direction. I decrease the angle between adjacent cabinets. And if I want to decrease the level in a given direction, I increase the angle between adjacent cabinets. It's as simple as that. And so this is what I'm going to do now. Okay, see, I'm going to open up here, maybe 5 degree. Let me see, 7 degree, 10 degrees, 10 degrees, and I carry on. And you see, I need many 10 degree cabinets up. So I can see it's not loud enough here. So maybe I should reduce the angle here in that direction down to 7. Maybe this is better. Maybe this one is 5 is okay. Here I'm a bit stuck. You see, I'm at 10 degrees. So I'm going to increase the quantities. Okay, I need at least 2 additional cabinets, which I'm going to take here, move to the bottom, and move this one to the bottom also. And let me go 10 degrees again and 10 degrees again. So this is what I do. It's a little bit hot here at the front versus the level I have at the back. So maybe I can reduce here to 3.5. I'm starting to be maybe here 5 or 5. Oh, this is, I would say this is, probably as good as I can do it. Maybe 7 was better, in fact. All right. And there is my cluster. Okay.
Also,
I can check. Yes.
Question sometimes comes up is why we don't work with autosplay.
Because autosplay cannot do what I'm currently doing. Very, very simply. I believe that how you want to spread the energy over the audience is the designer decision. You cannot leave that on the computer. Very simply.
So it's a kind of quality insurance thing.
It's a quality insurance. I think that when we work on such projects, Reinhard, you see, it's going to take me half an hour. The autosplay is not going to make it better. I'm not going to make it faster, right? And also, the autosplay has very difficult problems in managing this kind of situation where you have discontinuity, right? So don't expect this kind of process to be automated in a way that works. I'm very sorry to say that. It's when we design for sound systems, we have to make decisions, and these decisions are our decision. They're not the computer decision. Is that
experience, isn't it? It's knowing how the system works correctly for the right environment, and you can't ask AI to predict human condition.
Yes.
Yeah.
So you see, I can evaluate in dBA how much I'm going to have, you see, and I have something like 111 dBA. That's loud. You know, if I take off 6 dB headroom, it means that I'm at 105 or something like this. But anyway, so I've done a design with 9 cabinets. I could reduce the angles and put 12 cabinets and even increase the SPL. So let's look at this cluster, what it does, right? And I'm going to check for dBMIF. I'm going to check the coverage, all right? And this is the coverage of my system, right? It's exactly like in the cross-section view. I can see it's a bit loud here. Maybe I can optimize a little bit. But you know what? I believe that this is too much. I believe that I'm not going to fit into the budget because the SPL I'm delivering here is too high. So now I can benefit from the fact I have a 20-box, 20-degree cabinet. So let me redo the design, right? And let's evaluate here what I'm going to do, okay? I can go this way, and I can go 1220, and probably I can do it with 6 cabinets only. So I have 13 degrees here, 13, probably I can go 16, 16, 20, something like this, okay? And yeah, this is probably, let me see if I go 13 here, just to confirm. Yeah, this would probably be the nice design, okay? I let the level drop a little bit at the back. This is what automated could not do. And I do that on purpose because I might have reflective surfaces here. If I'm not happy with that, then I can eventually increase slightly by going this way. Okay,
it's also quite often at the back of those rake seatings are very, very close to the roof as well, which sets up a lot of reverberation going on.
Totally, Gareth. Yes, absolutely. So this is one cluster, right? Done. Okay, let's evaluate now the coverage, and let me evaluate the coverage with a little bit more accuracy. I'm going to go 1 point per octave, but I'm going to use 2 here as a resolution step. And I go start. Boom. And look at it. This is my coverage. And you can see something. This is the horizontal coverage. You can see that the coverage at the top, yes, is eventually slightly higher, wider than the coverage at the bottom. And this is normal because my cluster is closer to the lower stands than it is to the upper stands. So I also have this great feature here where my GOMs can be configured for a wider horizontal coverage. You see, I have 3 cabinets covering the upper stands and I have 3 cabinets covering the lower stands. So I'm going to increase the horizontal coverage on the lower stands. All right. So the upper stands are going to be 80 degrees and the bottom stands are going to be 120 degrees. And now I can check again. This is very fast. And you see my horizontal coverage now is looking much better. Yes, and much more consistent. Okay. So done. I have, like, see, my coverage is like a rectangle almost. So now I mentioned that I should look at positioning a second cluster somewhere between the 3 and 6 dB area. You know, and so I'm going to duplicate that cluster. That cross section, by the way, is the same. So I'm going to duplicate that cluster here. I'm going to offset. I forgot if it's X or if it's Y, but I don't care. I'm just going to, okay. And I'm going to put it on the same beam, probably somewhere around here. Okay, and I can check again for horizontal coverage. Okay, maybe on that beam here. Let's see. Okay, let's see if I have a, and I redo the computation. Perfect. This is absolutely fine. You can see I have something extremely smooth. They're not too close. If they were too close, I would have additional level here. Okay, they're the way they should be. And so then it's piece of cake. I go across X, and I'm going to have that cluster here. I take this one, I go across X. Okay, and I'm going to have my cluster here. And then this one goes duplicate across Y. And I have, okay, and this one is going to go, sorry, this one across Y, duplicate, and I go the same. And now you see the long stands are being covered. All right, so this is the coverage I have for the long stands. Okay, so now let's deal with south and north, east and west stands here. Okay, so again, I'm going to duplicate. It doesn't matter where it goes. Let me put 10 meters. I'm going to take it and I'm going to bring it here. Okay, So again, I go on the beam, I rotate it, and probably this one I will have to redesign slightly because the cross section is not necessarily the same. All right, so that's probably a right position, and maybe I'm going to go slightly this way, this direction. I can see that the spacing here is, so this is 0 and this is 15. So this should be around 7.5. Maybe I can put it a little bit closer so that I keep more or less the same. This is good. So this would be the position. Let me again adjust here the horizontal angle to be precisely at 0 and speakers. And you see, so let me open it wide. And you see, this cluster is not, I believe I'm losing a little bit too much here. So probably, maybe I can go 2 110s and 4 M20s, and let's check again. So this is going to be 7. Okay, this would be 10. This would be 16. This can probably go 20. And this maybe can go 16. Isn't it easy, Garrett? To be honest,
I don't know. I honestly don't know why we pay engineers so much money. I really don't.
So again, I have my 120 degrees here at the bottom, and that makes me realize that maybe I did a mistake here. Let me check again. No, it's okay. But when I duplicate it here, how come no, it's all fine. Okay, so I have that cluster. Again, I evaluate. So I can mute all of them, right? I go in the table here and I mute all of them. And I keep the last one that I just inserted open. Okay, and I check the coverage for that stand here. All right. It's a bit loud at the back, as I can see. So maybe I was a bit optimistic. So maybe let me go 10 degrees. And maybe here I could go 13. And maybe here I can go 16, something like this. So I've slightly modified, right? 7. I've slightly modified my displaying angles. And I mean, I know why. Sorry, this is because I'm in dB. Okay, I got it. Sorry, this is a mistake of mine. I should have been in dB MIF, not in dBA. So in this direction and in this direction here, probably I should go 10. This one 13 is difficult. This one could go 20 maybe. And this is, if I go 10. So in fact, you see, this is not bad. But you see, it took me to a wrong decision by not doing the things properly. But I think this is okay. I think this is, we can check again. And let's see. I think this is good. Okay. And so I'm going to duplicate. Okay. And I'm going to duplicate across X. And I have my second cluster. And I do here again. I repeat. All right. Beautiful. This is very straightforward. Let me do the opposite stand. So duplicate this time across Y. So it's here. I'm going to put it on the beam. So the beam is here. Okay. And now the side view is slightly different. So let me check again my side view here. And you can see clearly the upper stands are not going as high as they were in the past. So I have to go down here. Okay. And I believe that because what I have to cover is less, it could well be that 4 cabinets are enough. And this is 4 cabinets. And probably 80 degrees here and 120 here. Okay. And let me go again. So now I'm going to mute them all again, except the last one I've inserted. Close, and I check the coverage here. Perfect. Duplicate across X, second cluster. And now I can unmute everybody. Okay, close, and let's check the overall mapping. Let's check if the levels are consistent, right, for what I've done here. I think it's not bad. I think it's not bad. Maybe I can put an additional cabinet, you see, on the left stands, because it seems to me that the level is probably 3 dB lower. So going 4 was probably a bit optimistic. Let me go 5 and check again. So 13, maybe I go 13, 13, I go 16, and I go 16, something like this. And maybe, in fact, you know what? Maybe I should go 4 and 1, something like this. So 13, and here I go. No, probably I should go. Sorry, probably I should go 3 and 1. Let me check again. This is I'm really working so that I really get the same level everywhere. That would be 10. I said I need a fourth box. So this is going to be 16. This would be 13. Struggling a little bit here. This would be 10. And this would be 7. I think this is good. And the 3 bottom ones should be at 120, probably, and the upper ones. So let's check again. This could be more reasonable in terms of I delete this cluster, right? And I duplicate this one again. So you see, again, I don't want to be too insistent, but none of the things I'm doing could be done, you know, in an automated way. So let's check again. And you see now the levels that I have are more in line with the levels I have on the upper and lower stands, right? So this is where I am, and I can see now that I have to deal with the curves. I can see that the level is dropping on the curve. So I'm going to put a cluster probably here. Let me duplicate this one, offsets. Okay, so where is it? It's here. And let me put it at the crossing here. And let me try to put a little bit of sound in that direction here. Curves are always a bit critical, huh? Always. It's probably, let me take a position which would be somewhere like this. It's always a bit difficult to design for curves. So let's see what we're doing here. We have 10. Probably this one can be reduced to 16. It's at 120. And here I could go 7 eventually. And I can go 10. And let me go 13, that's okay. 16, 16. So I have to go back 20 here probably. This would be, I believe, okay. And I'm going to put them all at 120. And let's see now how this cluster is actually covering. And we can see the 2 opposite curves. So this is going to tell us, you know, how much that cluster is doing its job properly or not. What can I say?
Well,
okay. Yeah, we're definitely not. We're definitely paying you too much. It's too quick to
duplicates.
Great job.
Duplicates across X. So I have the cluster now here, and now I have to deal with this one over there. And you see the curve is not the same. So this one I'm going to use probably only cabinets to cover the real top part of it. So I can see that here, probably, you know, I'm going to go 1, and I think that 13, maybe, so the angle has to go down clearly. Okay, let me go 7, let me go 10. I put an additional 1, and let me go 10 again. 10 degrees. Okay, and again, they should be all at 120. I think this maybe 10, 10, 10. No, 10, 10, 10 is not good enough. So 7 this way is probably better. Let's evaluate and let's see.
I think that's the nice thing about NS1, that it allows you to play with your system design in real time, and very quickly. So yeah, you know, the workflow is very quick.
Yep. Okay, I can see that, you see, I have a little bit of the problem in that corner here. That's not an easy one. Let me rotate the cluster slightly into here, you see. And this is typical when we go into 90-degree corners. It's not an easy one. Because, so probably, let me go up again, and I can see now the upper corner. Maybe I should go this way. 7, 10, 10. I go 3 plus 1. And this one could go 13. Let me try that. Okay, all at 120. And I think that will be good enough. Yes, I think this is really the best I can do. So I now duplicate, and I duplicate across X. Okay, and my design for S12 is finished. Let me disable, just so that you show, let me disable this plane here so that we can look at statistics on coverage. Hello, come here. He doesn't want, but that's okay. That's normal because I'm in. And let me just disable the field for the moment. Let me do a quick, I'm going to run I'm going to go 3 here just so that we don't spend too much time. And let's do the mapping in MIF. Okay, so this is the coverage I've achieved. All right. I can evaluate now for DBA because the tender, I've worked on coverage with MIF, but now I'm looking at specifications and I want to check where I stand with DBA. I have 6 dB headroom here in my window. All right. So it means that this is the level I can achieve on music program, right? If it is pink noise, full power, I can go 6 dB above these values. Okay. So this is what I have in DBA, and I can look at the histogram. The histogram is very interesting. Look on the design I've done.
Nice one.
I have 41% of the audience is at 103 dBA, and 58% of the audience is at 105. So you see, I'm within 2 dB, 3 dB. Right, so the mean value, you see the standard deviation is 1.22. This is extremely small, and the mean value is 104. So I know that I can go there and I can play my system at 105 dBA without going into the protections. And I know that if I make measurements with pink noise all the way down into the protections, I'll be around 110. And remember, this is only direct sound. So I'm not taking account of the contribution of reverberant field. This is, I think, very important for us, NEXO. We commit, and we don't have a problem in committing to a value and giving more. We will never commit to a value and be below that. This is not something we can do and you can do. Okay, so what we have left now to do, we should deal with the pitch coverage, right? So let me deal with the pitch coverage is people who are standing, okay? And probably the best way here to do the pitch coverage is actually to use these clusters and to extend them right into the pitch. So let me show you here, okay? I'm going to mute these boxes, okay? And I'm going to put additional 1220s here, okay? And this is going to be 20 degrees. This is going to be 20 degrees. And this is going to be 16 degrees, right? And I have a -6 point at the center. That's in dBA. I should always look in dBA MIF. I keep on looking. This is good, all right? And yes, I want 120 degree coverage. Okay, so you know what? Let me delete this cluster. Let me delete this cluster and let me delete this cluster. I'm going to mute them all, except this last, I'm going to mute them all except this one. So I'm going to unmute my toggle. And now I duplicate 4 times. Okay, this way I duplicate across here and I duplicate across here. Okay, and so now I go and I check in dBMIF, I want to see the coverage of my pitch. So I've been using a total of 12 cabinets to cover the pitch. And you see, this is the coverage of my pitch, done. Okay, I have a, so I can evaluate again on the pitch, what are the values in dBA. Okay, you remember we were at we were at 104, 105, right? And now you can see the pitch here covered with 12 boxes, and covered with 12 boxes, I am more or less at 99 and between 99 and 102. So you see, this is what I mentioned earlier. we're typically 6 to 10 dB down on the pitch. This is only 12 cabinets, right? Versus it's 12 cabinets out of a total of 88. So I'm using 76 cabinets for the stands, and I'm using 12 cabinets for the pitch. So the pitch is done, right? Let me now unmute all these. I don't have to necessarily, so I can leave it this way. And now I should look at a sub design. So if I want to do subs here, I have two possibilities. One of the possibilities is to put subwoofers on all clusters. So that's a possibility. It's going to reduce the height a little bit. And it depends on the weight which is accepted per cluster also, of course. But doing that is probably going to give me a little bit of a interference pattern between subwoofers from one cluster to the next. So probably, and also because we're getting close to the end of our session in terms of timing, but I'm going to put a central subwoofer. So I'm going to put LS18s columns, and just a second, I go back to systems here. And in fact, I'm going to put GeoM subs, M sub 18s. So I'm going to put an M sub 18 flown at 40 meter. That's okay. And I'm going to put 6 of them. Okay, so this is what I have. And I have to position it and I have to rotate it. So it's here. I don't want to do any mistake here. This is my cluster. So I'm going to take it from where it is here and bring it here to the center. Okay. And I'm going to, let me see quickly. I should go 0 degree. Horizontal angle 0 degree. Okay. And let's check what it's doing. I go dB LF this time if I want to check. I go start. Okay. I'm in Omni mode. So let me go in cardio mode. I have 6 of them and we can see the effects. So that these subwoofers go this direction. And this is what I have. Okay, I'm sorry, I should have, I have some interference pattern because I did not mute all the speakers here. So I have to mute them all and I want to look at the sub only. This is why I had a strange pattern. So this is my pattern. You see, it's not bad, huh? It's, I'm within 6 dB for my subwoofers, okay? Eventually I can try a different, let me try a different cardioid pattern that is, in fact, to go on these, to bring the lobe up to see if I'm eventually slightly improving. And no, I don't think it's better. I think it was better the other way around. So I go back to what I had. Up, up. Okay, I go this way. This is one side. I duplicate across X, if I'm correct. Oh, this is wrong. So let me take it off and let me, in fact, readjust this one. GPS, this should be 0. And I duplicate across Y. All right, maybe they're a bit spaced apart. We'll see. I don't have too much interference, but oh, okay. This is what I have. All right, so I'm within. If I look at the histogram now to evaluate, you know, how my subs are falling. My subs, they go from in the sub range, they go from 95 to 100. So I have a subwoofer coverage which is within 5 dB. That's quite spectacular. Okay, be careful, of course. I'm not taking into account the reverberation of the room, but I have 12 subwoofers, which means that when I'm going to push extremely loud, yes, I will not necessarily, I will hit the protections of the subwoofer before I hit the protections of N12. So we always have to question in the sports arena what the subwoofers are for. If the subwoofers are here so that I can play the music extremely loud and the sub follows, I have to have a better ratio of subwoofers, more subwoofers. If it is only so that I have low frequency extension when I'm playing music at a reasonable level, then such design would be acceptable. Okay, and I can eventually, we can try something, although I'm not sure it's going to work, just to finish. So I'm going to go 2 meters here and where is the one? It went this way. Let me try to make a See a quadruple of subwoofers. It's just a tentative, huh? 0. This is going to be 1.2, and this is going to be 90. Okay, and I go duplicate across Y, cross X. Yes, and let's check again, just quickly to see what we've done. Oh, look at that. This is really, I think this is really the best we can do. You see, the subwoofers are so close one next to the other that I have little interference, and the fact I've set them on cardioid makes it such so that the one that is on this side doesn't interact with the one on this side, right? So that's probably, and then when I go, I could do that later on, but what I have to do now is time align each cluster here with that central point, okay? And so that I actually have good phase relationship between that central cluster and all the speakers which are in the crown way all around. This is so good that I'm going to save it for next time.
Yeah, expect to see this design reused at a stadium near you very soon.
So this is let me stop sharing here. So this is this was a practical aspect. Of course, the next step, but time is too short here. The next step would be to export that model into ease and then look for the STI values once we have reverberation time and background noise, and then generate and do some kind of a PDF document which is going to specify the cabling, which is going to specify the switch, the network architecture. This is the things we do at engineering support. Is we've been looking mostly here on acoustic design, but we also look, of course, at electrical design, cabling, network, everything, rigging, mechanics. We look at all these aspects because this is what is important for a project. But anyway, I hope you enjoyed the show. And Garrett, we leave the last word on you.
Well, we've got no outstanding questions. At all, which is great. Bert did make one point that I answered. I typed an answer for, which was that designing stadiums is should be a very specialist pastime, not for everybody. And I would just encourage anybody that's involved in a stadium to contact engineering support at NEXO, either directly or via sales manager, because we, never think you're wasting our time by bringing a project to us, because we are always happy to help, no matter how small or how big. We will always assist everybody in their designs. We've got another question from Bert, who designs the rigging.
I interrupt 2 seconds. I interrupt 2 seconds.
Yeah.
Of course, Garrett, we're very happy to assist you from day one on the design all the way down to the success, and that drives us also very happy.
Yeah. So Bert has asked who designs the rigging for these special applications, where we've got custom rigging being put into the roof of varying stadiums.
Bert, the service we offer is the following. The regulations for rigging and winds vary from one country to the next worldwide. So we cannot design because we don't have these regulations worldwide. So we don't do the custom rigging design. But we support it. It means that when the rigging design is done by the contractor, because it has to take higher wind velocities, we submit this design to our structural engineer, the same person that does the third-party company that does all the computation on the NEXO rigging system. He's going to take a look and he's going to take some advices, and he's going to say, yes, no, you should do this or you should do that. But final responsibility is for the designer because of local standards and regulations, right?
Yeah, and if I can just add to that, everybody, system integrators around the world come across these projects and would like to get involved in these projects because they're seen as being large order value and everybody makes lots of money. Not necessarily the case. But if you are working in an area where you are not experienced, I would really encourage you to maybe form a working partnership with a system integrator that does have the necessary experience for designing that sort of rigging material. It's certainly something in the past 10 years we've done in the UK, where we've brought two different companies together to work as a consortium on a project to make sure everything is done in a safe manner, because everybody has their area of expertise. So again, if you've got a project and it's something that you think, I'm not quite sure if I can do this project, talk to NEXO, and if we've got another partner you could work with, we'll make the introductions and try and make that work for you. So, you know, whatever the question, pick up the phone, speak to us.
Bert, just to complement Garrett's comments, of course, the expertise and the skills of the contractor is essential. The custom rigging, however, keep in mind, it's only for outdoors. It's not for indoors. For indoors, I believe the hardware of NEXO is going to cover all cases under certified conditions. It is the wind that, in fact, changes the regulations worldwide. It can be wind, and it can be, well, everything which relates to the outdoor environment in a general way. It could be in Japan, for example, or in Mexico, it could be earthquakes. You see, so you have all these things that you have to match and adapt to. Anyway, thank you, Garrett, for complimenting.
Always a pleasure.
Thank you very much, Reinhard, for being with us for this whole session. Reinhard is also very experienced in sports arenas, and anyway, nice projects to come worldwide. Anytime you want to visit one of the arenas that is equipped with NEXO, feel free. The references are on the website. We have wonderful references in worldwide, basically, as I mentioned, Japan, Belgium, France, UK, Germany. We have, you know, wherever you are, we have a nice sports arena to take you to. And anyway, be well, all of you. Thank you again for spending that much time with us, allocating that time to us today. Don't hesitate to get back to us if you have, again, as Garrett mentioned, specialized questions, or if you would like to have more in-depth sessions, you know, on specific topics. We'll be very happy to support you on that. And we look forward seeing you soon.
Okay. Thanks for joining us, guys.
Thank you very much, everybody, and be well. Bye-bye.
Take care.
Bye-bye.